Thank you for joining us today. I'm Dave Cocking and I'm joined by DesignBuilder's Managing Director, Andy Tyndale, who will help answer your questions at the end. I'm very pleased to say that today we're also joined by Matt Rash and Jim Dirks. Matt Rash is a Mitsubishi multi-applications engineer with 8 years manufacturer experience of variable refrigerant flow, or VRF technology. Prior to that, Matt's background was in architectural and engineering consultancy, where he designed HVAC systems for commercial, healthcare and institutional facilities. He was also involved in ASHRAE 90.1 energy analysis and auditing facilities for energy saving improvements. Matt has a broad and in-depth knowledge of the HVAC field and is very excited about applying this experience to help others utilise the full benefits of the growing VRF technology. Jim Dirks is the CEO and founding member of the Building Performance team and loves to provide greater understanding to commercial building owners about how their building's performance affects their company's productivity and bottom line. Jim's been involved in the design, commissioning, analysis and modelling of HVAC systems since 1975. And is himself delighted when he's able to delight teammates and clients. That'll resonate with many of you from reading Jim's many useful forum posts. He believes that high-performing buildings allow people to enjoy greater quality of life than they might otherwise have, and is proud to help his clients reduce overhead and improve competitiveness. Over the next hour or so, we'll introduce you to the latest thinking regarding VRF design and simulation, aiming to give you 3 different perspectives on VRF systems and how to model them. There'll be time at the end to answer your questions, which you can submit at any time during the webinar via the questions box in your control panel. If you have a question, I'd be grateful if you could start it by saying which of the presenters it's addressed to. Our first presenter will be Matt, who will boil down the important aspects of VRF technology and discuss typical applications. I'll then provide an overview of how VRF systems can be modelled in DesignBuilder. And finally, Jim will discuss some important considerations in VRF design and modelling. I'll now hand over to Matt.
Well, again, I want to thank everybody for having Mitsubishi here today. We appreciate everybody taking time out of their busy schedules to be present on the webinar as well. And so we hope it provides some valuable information revolving this technology that's emerging in the industry. So the goal today is to provide a quick, brief overview of this technology, some of the application considerations, advantages, efficiency savings, and then really finally summarize some of the important factors that need to be considered when trying to assess actual performance of these systems throughout the course of the year in particularly commercial building applications. First off, I know a lot of people are familiar with this technology and it's growing in many world markets, but I think there's still quite a few folks in the design community that haven't been exposed to this as readily as others. So I think it's important to take time and provide just a quick brief definition of what is VRF. So in simple terms, when we say VRF, we're talking about a multi-zone split DX system, multiple indoor units connected via a common refrigeration network to a single VRF outdoor condensing unit. That condensing unit may consist of multiple modules that are twinned together, but they all share a common refrigeration network. Among this VRF, particularly commercial class equipment, all of these systems have the capability to provide cooling and heat pump heating operation, and with a far greater extended range that we'll illustrate later in the presentation. Also, that's unique to these systems is the ability to provide simultaneous heating and cooling, where some zones can be in cool and others in heat, and energy is transferred or shared via that refrigeration network, increasing the effective efficiency of the system in those simultaneous modes. You'll hear terms such as 2-pipe versus 3-pipe. This really comes down to the distinction between the Mitsubishi heat recovery system and the majority of other manufacturers' heat recovery systems. Mitsubishi uses a 2-pipe variation. Other manufacturers actually use 3 pipes, but they're essentially accomplishing the same process, and we'll talk about that later as well. Unique to these systems is also variable capacity control at each of these DX coils. They have smart coil technology. So each of these units will have a linear expansion valve, basically a pulse needle valve, with up to 2,000 steps of operation. And that provides very precise throttled meter control of refrigerant to each of the indoor units at any given time. With that, the outdoor unit responds to that varying load with a variable speed scroll-driven compressor technology. And with this technology, you'll see high turn-down ratios, below 10% in many cases. There's also a great deal of flexibility. There's a multitude of indoor units that can be attached to these systems, up to 50 depending on the size, and they range from ducted to non-ducted to the conventional wall mount units that we think of in terms of mini splits. And then probably lastly, the most important thing is the proprietary packaged DVC controls that's contained in these systems. That's what allows all these devices to operate efficiently and effectively together to realize that energy savings potential without relying on complicated third-party controls that need to be installed in the field and maintained throughout the life of the building. Again, at the heart of this technology is that inverter-driven scroll compressor. So the ability to ramp up quickly and then modulate and maintain set point over long periods of time, elimination of those cyclical lows associated with conventional stage DX equipment. In terms of evolution, this really is a new technology. This has been commonplace in Japan for 25 plus years and throughout parts of Europe for 20 plus years as well. It's been in the US since 2002. It's still a small percentage of the total HVAC market, but it continues to grow year after year and is making large strides in other countries as well. Looking at typical range of available VRF systems, on the air-cooled side, you're going to see up to 30 tons or in a range of 21 to 106 kW. This is strictly 3-phase equipment on the commercial side that we're dealing with. There's also a water-cooled variation of the VRF system, and everything downstream on the refrigeration side is exactly the same. Same flexibility, same connection combinations available for indoor units or similar combinations. The only difference being that you're exchanging, rejecting, or absorbing heat from that water side heat sink. And you'll see ranges in that from 21 up to 106 kW depending on the manufacturer. What's also important to note about those is their wide temperature range. Typically they have ratings between 23 and up to 110 degree condenser water inlet, so perfectly well suited for geothermal applications. There's also a single phase line that most manufacturers carry that's going to be in the 10 to 18 kW range. That is strictly a changeover line. So one thing I didn't mention is most manufacturers have 2 variations. They have a changeover system where all the zones have to be in the same mode at any given time. And then they have a heat recovery system variation that allows that simultaneous operation with heat recovery. On the single phase equipment, that's not available typically. You're just dealing with changeover. Again, looking at basic system components, you have the outdoor system, the air-cooled heat pump, or in the case of the water source module, which will be located inside. Then you have your main refrigerant pipes from those units to the very first thing they would see in these heat recovery systems is a branch controller or controllers. There could be more than one. From that branch controller, you'll have separate lines or dedicated ports, I should say, that feed the dedicated circuits to each of the indoor units. That branch controller doesn't provide the throttling, though. It just provides and dictates the mode that's available to a respective indoor unit or the state of the refrigerant that's available to that indoor unit. All the throttling and all the logic is comprised within the indoor units themselves. In fact, these systems can be installed without any additional controls. That's usually not recommended, but again, that logic is contained within the equipment. You can go a step further, which most people do in most applications, and apply what we call zone remote controllers that you can locate on the wall, give you interface capability to the indoor units in the system, also provide remote sensing capability closer to the occupied zone. And then you can go up to higher levels to what we call system controllers that can control multiple systems with multiple indoor units, and then even a step further into lawn talk and backnet gateways to integrate these systems into conventional building management systems by third parties if need be. Again, looking at the piping layout, in the case of Mitsubishi's heat recovery system, you'll have a high and a low pressure pipe from that outdoor unit to the branch controller. Inside of that branch controller are several devices. One of the most important ones is a gas liquid separator. That's what allows the separation of states when you're in a cooling dominant heat recovery mode. And then there are some tube-in-tube heat exchangers inside of that device that actually provide what we call medium pressure liquid. And that is your cooling liquid that is being subcooled that's sent out to indoor units and cool when you're in this cooling dominant heat recovery mode. Looking at the BC controller in this dark dashed line, which is what's represented on the screen, again, you can see some of these major components: the gas liquid separator, the tube-in-tube heat exchanger. We're not going to spend a lot of time talking about this, but I want you to be aware of it and just know that there are additional tools available that can help walk through the refrigeration flow diagram in greater detail. The important thing to keep in mind is you're dealing with those three states of refrigerant. And again, when you're in a heat recovery mode, specifically the cooling dominant mode, what you'll actually see from the outdoor unit is a mixed phase refrigerant coming into that gas liquid separator at point 1. And again, that's what separates off those two states and feeds the hot gas to the indoor units in heat, and then medium subcooled liquid, medium pressure subcooled liquid to the indoor units in cool. Also, what's unique is when you have units in heat, that liquid is recovered and brought back to this BC controller and actually sent back out to units calling for cool. So that liquid is reused in series, and that's the mode, the mechanism of heat recovery. Again, when you look at three pipe variations from other manufacturers, they're accomplishing the same task, but they're actually doing that back at the outdoor unit. So you'll see three individual pipes. Again, those three pipes representing those three different states of refrigerant: low pressure suction gas, a high pressure gas for heat, and a medium pressure liquid. And again, they'll run those three pipes throughout the entire building down to the farthest run, and then branch off of those each time with a branch selector box. Again, that box is only dictating the state of refrigerant to the indoor unit based on the mode it's calling for, and the indoor units would throttle, just as the indoor units in the Mitsubishi system would throttle through their built-in linear expansion valve. So very similar, it's just accomplishing those tasks in different locations. In terms of target applications, all of these pictures on this slide represent applications, projects where VRF has been installed successfully and continues to claim greater market share of these common commercial institutional type applications. I think a couple applications to look out for that really aren't suited to VRF is when you're dealing with invasive procedure, classified type clean rooms, classified type laboratories. Because of the decentralized concept around these systems and the low fan power consumption, the indoor units typically don't have significant static pressure capabilities to overcome HEPA filtration. And then certainly in process or caustic type environments, the equipment's really not suited for that. There's the materials and the coating methods aren't suited to harmful environments like that, so that's something to stay away from. Again, originally coming in the market, I think VRF had a niche application in more of the retrofit, historical renovation type projects, and that is because of the space saving advantages. But as I mentioned, it's extended into other areas of the commercial market and proves to be a viable option. But in terms of transport energy requirements, VRF is really one of the lower system choices, aside from the space savings advantage. So if you look at a centralized air handler, for instance, on a small 20-ton system, you're dealing roughly with a 40-inch by 20-inch ductwork. Again, you've got typically longer duct runs, higher external static pressure, and in return, higher fan energy costs. And consequently, historically, fan energy is probably one of the biggest contributors to energy consumption in commercial buildings. You can move into a hydronic system, such as a 4-pipe chilled water, hot water fan coil system, and take advantage of significant space savings, but then you're incurring those high pumping costs associated with that transport energy. So again, moving into VRF, moving that refrigerant medium through the building as a means of transporting energy, taking advantage of that latent heat phase change that's just inherent to the refrigeration cycle. That's always your lowest operating cost and most efficient means of moving energy through a facility. In terms of integrating outdoor air into these systems, most of these indoor units have fresh air connections on them, such as the cassettes or one-way ceiling-mounted cassettes. All manufacturers have a multitude of different ducted type units, and again, fresh air can be introduced into the return ductwork, similar to how fresh air would be introduced into water source heat pumps or four-pipe fan coils. More commonly than not, though, a dedicated outside air system is being applied to at least temper or partially temper air before it's delivered to these indoor units or to the space, or at least at a minimum an energy recovery type ventilator, whether that's a larger centralized or with a wheel, or a decentralized unit with a fixed core. Some of the advantages, though, I think are important to note when applying DOAS systems, because those are the most common application of fresh air with the VRF technology. I think number one is the potential reduction of total corrected ventilation rate per ASHRAE 62 methods. When you're dealing with centralized air handler type systems, you have to penalize and correct your total outdoor intake flow based on the worst case zone. So there's a penalty factor associated with that. By decoupling that fresh air and delivering it direct to each of those spaces, that allows you in many cases to reduce the total corrected outdoor intake. Second, I think the ability to easily shut down ventilation in occupied areas. When you're providing DOAS units, especially decentralized DOAS units, and a lot of VRF manufacturers offer that or are beginning to offer that. In a lot of cases, they're units that can connect to the VRF system or are their own variation of the VRF system themselves. That allows you to shut off certain areas of the buildings that aren't in use for large hours out throughout the day. And then, of course, you can move into larger centralized DOAS systems, and for buildings with high occupancy density, take advantage of VAV controls with real precise demand control ventilation in those high occupancy areas. Third, the ability to incorporate supplemental heat zones, and this is very important. A lot of designs with VRF, the DOAS becomes a means of getting supplemental heat into all the fan coils under those extreme winter periods, and this can really help with the outdoor systems in terms of recovering from defrost operation under those extremes. So it's not uncommon to see DOAS system heating coils oversized for 120-degree plus discharge air temperature. And then the ability to allow the indoor unit fans to cycle, I think, is another important advantage if applied correctly. If you're completely decoupling that air from the fan coil itself, the VRF fan coil, then that fan coil can be set up to cycle its fan when thermally satisfied and take advantage of additional fan energy savings. Most of these fans are very low power consumption to begin with, and they do have auto fan modes which step through their speeds, high, medium, and low in response to demand. But in a lot of cases, low speed is still 70% of high. So allowing those units to cycle off if you decouple that fresh air completely can also offer significant savings. And then lastly, and just as important, I think, is improved part load dehumidification control. With DOAS systems, typically you're providing actual dew point control of that discharge air and targeting the dew point at or below space conditions, removing all that latent load from the outdoor air and potentially some of the latent load generated internally from occupants, and maintaining correct humidity levels even during those part load off-peak rainy days. In terms of heating capability, this is where VRF really brings in a large advantage when comparing it to conventional air source heat pumps, and that's really represented by that line on the left, that blue-colored line. You'll typically see D rates close to 60% at around minus 8.3 degrees Celsius, and that's typically a lockout condition. These curves on the left represent VRF technology, and it varies depending on the make and manufacturer. But you can see typically across the board between all manufacturers, actual tested guaranteed rating data down to minus 20 C. And then if you move into what's called flash injection scroll technology, which a lot of VRF manufacturers have, that allows you to achieve actual guaranteed test data down to minus 25 C with heating capacity up above 80% in a lot of cases. And the other thing important to note is this is not a thermal lockout condition where these graphs end for VRF. that is strictly just the end of their rating conditions, they'll continue to operate typically down to -28°C. Again, looking at the efficiency effects from the VRF system, the superior part load performance, again, that's attributed to a large part that the inverter-driven scroll compressor, variable speed compressor, that variable capacity indoor unit control, that smart coil technology. Again, each of those units have that linear expansion valve precisely throttling the refrigerant at any given time. And then again, the system intelligence, that packaged DDC control that allows all those units to operate both day one and throughout the life of the equipment at their most efficient, optimal level. But the last three items in red are really the most important, and this is really where a lot of the savings come into play, is the heat pump capability, that extended air-to-air performance. And that's going to depend heavily on the rates and the fuels you're comparing to, but in a lot of cases, that's a good chunk of the savings, especially in heating-dominated climates. Second, the heat recovery during simultaneous cooling and heating. And again, the thing to point out is the ability to recover heat not just during cooling dominant modes, but also during heating dominant modes. And that's kind of distinct and different from other conventional systems. And then lastly, the fan savings tends to be one of the bigger components, as I mentioned before. Again, it's this 50-50 balance point, though, when you're in this recovery mode where your system efficiency can really skyrocket. And the problem with this is most systems don't operate at this point all the time. And in fact, the percentage of time that they spend operating near that point is very dependent on building application and the grouping of zones. In fact, in these simultaneous heat recovery systems, we usually recommend people group in an equal percentage ratio, internal with external, to try to harness that heat recovery potential and maximize those hours where you're approaching that highest system efficiency level. And this is really where the need for energy analysis tools come into play, because again, that is so dependent on the building profile and the specific project location and how those zones are grouped. So when looking at energy modeling analysis tools, there's really some bare minimum, I should say, requirements. And this is by no means all inclusive. There are other factors and derates that have to be considered on top of this, but these are bare minimum points that have to be incorporated into an analysis tool. I think the first one is the incorporation of PLR curves, or part load ratio curves. You'll see a part load ratio curve for cooling performance when the VRF system's in cooling. That's percentage of full load based on, or percentage of full power, sorry, based on percentage of full load. And then also you'll see a curve similar to that for heating operation. On top of that, then, at every hour, you need the ability to accurately apply ambient modifications to this. And that'll be based on both outdoor ambient entering conditions and evaporator inlet conditions. And then third, the one in red is probably the most critical, is the ability to analyze the system at every hour and determine if it's a cooling dominant or heating dominant mode of operation. Because the dominant mode is what dictates the energy consumption of the outdoor unit. It's not being penalized for both. The minority is happening via heat recovery in that refrigeration circuit that we talked about. And that really ties into the last one, is the ability to account for heat recovery both during heating dominant and cooling dominant modes of operation. Again, these curves, this really isn't anything new. The part load ratio curve, percentage of full power versus percent of full load. You'll see this for cooling. It's a nominal curve. It's based on a 95-degree day, or 95-degree test condition, I should say. And again, there'll also be a curve for heating part load operation, which is based on a nominal 47-degree day typically. All manufacturers then publish these ambient modification curves. Again, those have to be applied on top of those PLR curves. They may be in the form of graphs or a family of graphs or charts that you see, such as this, or they may be tabulated values depending on the manufacturer. Mitsubishi tends to provide it graphically. And again, it's a family set of corrections based on outdoor conditions and evaporator inlet conditions. And you'll have two graphs for cooling power and capacity correction, and then two graphs for heating power and capacity correction. So to put this in perspective and just provide a real quick basic illustration, let's look at a simplified example. We have a small office building. It's at an ambient temperature at a particular hour of 10 degrees C. And it's being served by a 6-ton or 21 kW nominal simultaneous system. At this particular hour, and we're just taking an hour snapshot, we have a total load of around 7.9 kW cooling, and then a heating load of 6.2 kW. Again, the dominant load at this hour is the cooling load, 7.9. So that's what dictates the compressor operation and the demand from the outdoor unit, not the heating load. So if we start looking at these ratio curves, if we were at a fully loaded state on a 95-degree day, we would consume around 21 kW, or excuse me, 6.48 kW. Since we're at a reduced load state of 7.9 kW cooling load, that correlates to 2.38 kW roughly. Now again, this is at a 95-degree day, and we have to apply those ambient corrections. So where normally we would consume 2.38 kW at that 95-degree day or 35-degree Celsius day. At this condition, since at this hour was 50 degrees, that equates to roughly 1.87 kW. So what does this mean? We've just gotten 7.9 kW of cooling, 6.2 kW of heating. We've only spent 1.87 kW at the outdoor unit. Again, that includes the compressor energy and the condenser fan and some minimal losses for piping. That equates to a calculated efficiency at this hour of 25.7 EER or 7.5 COP. Again, this is an idealized situation because we're close to that 50-50 balance point. And again, that's going to be your highest efficiency level. And it's not uncommon to see this equipment cataloged and listed this way, especially if you look at the AHRI directory and start looking at ratings such as simultaneous cooling and heating efficiency, which is really just an effective EER when you're in that 50-50 balance point, that idealized balance point. So now, will you be at this every hour? Of course not, and that's going to, again, depend heavily on your building and your application. And that's really where the need to have a tool that can accurately analyze these systems throughout the course of the year really becomes important. So with that, I want to hand off the presentation to the next presenter, and they can elaborate on how these systems can be analyzed further with the DesignBuilder and Energy Plus engine. Thank you for your time.
Thanks, Matt. I'm sure many of the modelers attending will benefit from a much better understanding of the equipment and the different ways that the manufacturers can achieve heat recovery. I think the potential efficiencies of operation in heat recovery mode are very attractive, as you showed on your last slides. I'll now cover the DesignBuilder modelling aspects in this second part. For those of you not familiar with DesignBuilder, it's a graphical front end which gives you access to the power of industry-leading simulation engines like Energy Plus and Radiance, but in a much easier and more time-efficient way than modelling using the natives tools such as the IDF editor. DesignBuilder's interface also enables you to use other simulation engines. For example, to run energy performance compliance calculations for different countries in Europe. This means that you can run different calculations using the same model geometry and data simply by changing the analysis mode. So for example, you can see how changing glazing details affects both daylighting performance via radiance and thermal performance via Energy Plus using the same model. DesignBuilder also has its own CFD engine, which is fully integrated with the modeler, allowing you to use the same model geometry to run CFD simulations. You can link thermal simulation outputs to create boundary conditions for your internal CFD analyses. In addition to providing powerful geometric modelling tools, DesignBuilder's user-friendly interface and efficient data management system significantly reduces the amount of modelling time required. These qualities help to reduce the risk of modelling mistakes and make you more productive. Here's a very simple model I created earlier with north, east, south, west and core zones. The geometry will result in year-round cooling load in the core zone, but during colder periods we'll get good conditions for VRF heat recovery, which you'll see in our results later. I'll leave most of the model data at default settings and focus only on the HVAC related data today. Before considering VRF systems in detail, it's worth pointing out that DesignBuilder has two primary HVAC modelling methods, one simple and one detailed. The basic premise with DesignBuilder is that the model starts with the most simplified settings and you add complexity only when it's needed or appropriate as the design and model matures. The simple HVAC method is very easy to define and quick to simulate, and is ideal for early stage analysis to gain a sense of the energy flows associated with HVAC systems without having to model them in detail. The Simple HVAC tab allows you to quickly define typical systems by selecting them from a predefined list, as you can see here. All you then need to do is define some basic parameters such as the ventilation details, fuel sources, and system efficiencies. While Simple HVAC is perfect for quick testing or early stage analysis, there'll clearly be many occasions when it's not sufficient. In that case, we need the more detailed HVAC analysis mode, which I'll introduce now. We switch on detailed HVAC here in Model Options. I can then go to the HVAC system by selecting it here in the navigation panel. Initially, you'll see this thumbnail view of the default system or last system loaded with options to load one of the templates, but you could cancel out of the template selection dialog if you prefer. Although templates are typically the easiest and quickest HVAC definition method, you can also create your system by connecting individual components, or load a template as a starting point and then configure it to meet your needs. Here's the growing library of pre-configured templates, enabling you to quickly load typical HVAC systems to your model. You can also create your own templates and add them to the library should you want to. At the top, you'll find the 10 pre-configured ASHRAE 90.1 baseline systems and a couple of domestic hot water systems, including a solar thermal variation. Our range of pre-configured HVAC templates covers the most typical systems, including a variety of air source heat pumps, constant volume air systems, chilled ceilings and beams, various DOAS and fan coil systems, ground source heat pumps, a range of VAV systems, and at the bottom of the alphabetic list we have the available VRF templates. VRF is typically used in conjunction with a dedicated outdoor air system or DOAS to provide the required ventilation air. The DOAS system might have heat recovery and some form of demand-based control, depending on the climate and internal loads. We'll now use the VRF with heat recovery and DOAS template to explain some of the key concepts associated with VRF modelling in DesignBuilder. The schematic of the VRF system shows it simply as the outdoor unit connected via refrigerant pipework to the indoor unit. This can be used to model a standard two-pipe system or a refrigerant heat recovery system. Jim will talk more about the finer points of successful heat recovery installations during his session. Before looking at the component parts of the system, I'll explain DesignBuilder's zone group concept. In this case, the schematic diagram shows a single zone group served by the HVAC plant. All zones served by the same HVAC system are grouped together. If I navigate to the zone group, you'll see all zones represented. Using zone groups in this way simplifies the schematic, which would otherwise get very complex for a building with many zones and HVAC systems. Going back to the VRF system, we'll now take a look at the outdoor unit edit options. In the Outdoor Unit General tab, we can define system parameters common to heating, cooling and heat recovery systems. The default template is this Energy Plus example. This system is generic and good for early stage modelling when you may have no data. It also has the significant advantage that it's fully auto-sizable. Jim will show you data for a Mitsubishi system he's configured with manufacturer's data a little later. We also provide a small range of manufacturer's system templates, but for detailed VRF modelling you'll generally need to create your own system based on current manufacturer's data. As always with Energy Plus, there are many data inputs to model HVAC systems in detail, so I'll show you a couple of points of interest without going into too much detail. The minimum heat pump part load ratio setting is the operating point below which the unit will cycle on and off. Above this point, the inverter will vary the compressor speed at each time step to meet the load, improving the efficiency of VRF compared to traditional non-inverter systems. There are a range of control types that can be used, and these are explained in DesignBuilder's fully integrated searchable help file, along with all the other VRF inputs. At the bottom of the General tab, we can select the condenser type, which can be air, water, or evaporatively cooled. Going to the Cooling tab, I can access the cooling specific data such as the rated capacity and COP, amongst other things. No doubt you'll by now have noticed the number of curves. To model a VRF system accurately requires the use of a number of curves to determine performance at each time step, and these differ for heating, cooling and heat recovery. You'll see a visual representation of the curves here at the bottom right of the screen, which can help you make sense of what's going on, rather than just seeing a bunch of coefficients. It is possible to simplify VRF modelling where appropriate by selecting the single curve options. Jim will discuss when it might be suitable to use those single curve simplifications later. The generic curves provided are fine for the Energy Plus example system. However, when inputting data for a manufacturer system, you'll generally need to create your own curves. In order to accurately model VRF systems, the extensive curve sets are necessary. There's no getting away from the fact that creating all the coefficients required to produce 26 curves is a fairly onerous task. To make that easier for you, we've produced our own curve generation spreadsheets, which anybody can download from our website for free. You don't need to be a DesignBuilder customer. Here's an example of one of the spreadsheets. The first tab relates to piping correction factors, and you can see that detailed instructions are provided to help you make sense of the inputs. In the second tab, you input data for the capacity ratio curves, as shown here. Below the data input table, you can see the capacity ratio boundary curve generated that governs how the VRF equipment operates under higher and lower temperature conditions. Again, Jim will expand on the use of curves later. That's probably sufficient just to give you a flavour of the spreadsheets for now. The heating tab inputs are very similar to the cooling tab. And here in the heat recovery tab, you can see that heat recovery is switched on in this example by default, but you could of course switch it off. We'll now take a look at the zone terminal unit options. The zone terminal unit is a recirculation only device in this configuration, but you can add a direct air supply to the VRF indoor unit should you require. The indoor unit comprises of a fan and 2 coils. And as with all HVAC systems, you can navigate to and edit all components. A real VRF system has only a single refrigerant coil in the terminal unit. So one terminal unit can only ever provide heating or cooling at any instant. Energy Plus represents this as 2 coils, and they're commonly termed changeover coils, meaning that they operate sequentially but never simultaneously. DesignBuilder's implementation is therefore consistent with Energy Plus's representation. Here you can see the various options available for the whole terminal unit, which again is fully auto-sizable. Here's the option to specify a direct connected outdoor air supply. This is now clearly shown in the schematic. This option has very limited control and no airside heat recovery. A DOAS system, as we're using here, is much more efficient and controllable, so is generally preferable to this direct air option. Should you need to modify the indoor unit data for specific zones, you can change the parameters, then use the Target tab here to select which zones your changes apply to. The data for the fan and coils in the indoor unit are also editable. Here you can see the options available at coil level and the options available for the indoor unit fans. The final element of the HVAC system I'll look at briefly is the DOAS, which in this configuration is a simple system with heat recovery. The schematic shows that the air handling unit, or AHU, has inlet and exhaust dampers, a preheat coil for frost protection, a heat recovery device, and supply and exhaust fans. The configuration of the AHU will depend on your climate, and you can easily add heating and cooling coils and humidity control components to the AHU should you need to. The system configuration shown is fine for moderate climate conditions where the heat recovery device will ensure that the supply air temperature doesn't deviate too far from the zone set point temperature. The schematic shows the air loop supplying and extracting air to the zones via simple supply and return air grills in the zones. Should you have more than one zone group, where for example you have a central ventilation system but multiple VRF systems serving different parts of the building, the DOAS system could also supply those by adding connections via the air loop splitter and mixer. Going to the AHU edit dialog, in the General tab, I can schedule the AHU. Here I'll set it to operate from 7 AM to 6 PM Monday to Friday only. Here in the Outdoor Air tab, I could specify parameters such as an airside economizer, but clearly that's not relevant to a DOAS system, which is only sized to meet the ventilation requirement. Most of the options here relate to the heat recovery system, which I'll leave at default. I'll now run a simulation to compare the performance of two different VRF systems to highlight new features in our Simulation Manager and Results Viewer tool. If you're not aware, DesignBuilder's Results Viewer is another free resource which is again available to anybody who wants it via our website downloads page. It enables you to see Energy Plus node data, so is invaluable for confirming the correct function of HVAC and other systems. It allows you to see data like the temperature and mass flow at the inlet and outlet of components like coils and mixers. I already have a result set prepared for the same Energy Plus example VRF system with heat recovery switched off. So I'll run a new simulation using the same system but with heat recovery switched on to enable direct comparison. Going to the simulation calculation options, I'll give the calculation a meaningful name and run a quick winter design week simulation generating hourly results. I'm simulating the winter design week because, depending on the loads in your building, zones you may see no heat recovery unless you have reasonable heating and cooling loads. In this case, the core zone has high internal gains, so will need cooling, whereas the perimeter zones will require heating, so we should see a good effect. The Simulation Manager allows you to queue and run multiple simulations in parallel on your local machine, on a network server or on the cloud. This has many benefits, including freeing up the local machine to enable you to continue working on the model during simulations and to store and list result sets. One of the improvements in version 4.5 is the ability to load multiple result sets directly from the Simulation Manager to the Results Viewer. This gives you the ability to quickly load data for all result sets into one graph for direct comparison. I'll load the total electricity consumption for the whole building for both result sets simultaneously. The only difference between the two results is the VRF heat recovery. The results clearly show that heat recovery is beneficial, particularly at startup first thing in the morning, when there's the greatest differential between the core cooling load and the perimeter heating loads. So that basically covers all the main points relating to modelling VRF systems in DesignBuilder and using the Simulation Manager and Results Viewer to analyse results. I'll now hand over to Jim, who will explain more about VRF design for effective heat recovery and some of the finer details relating to VRF curves.
I'm going to start the portion and describe that the efforts we use as energy modelers are similar to what a martial artist would term the progression of belts. You start as a brand new martial artist with a white belt, which means your brain is empty or you don't know as much, and you progress through a series of colors and eventually become a black belt. This concept was applied to energy modeling by Ellen Franconi of the Rocky Mountain Institute, and I like it because there's clearly a progression in skills, and you grow and grow and grow. And by the way, in the martial arts arena, a black belt is sometimes described as high school graduation. So it's certainly not university studies and it's not graduate studies, but it indicates that you have a degree of competence and you have learned a lot since the beginning times. We're going to cover some black belt ideas here. Energy Plus itself is a black belt software tool, and I think one of the key benefits of Energy Plus is that it's frequently updated, and you can, because of those frequent updates, model almost anything without a workaround or some sort of alternative, hopefully equivalent scheme. Most things can be modeled directly within Energy Plus, and VRF, including heat recovery, is one of them, and it does it very well. If you want to stretch the capabilities of Energy Plus, the native capabilities, you can do so with a built-in programming language called EMS. That's also a helpful feature, and it's certainly a black belt capability. Back when I started using Energy Plus, the GUIs were pretty, they didn't have so many capabilities, and DesignBuilder in particular has improved by leaps and bounds in the last number of years, and it continues to improve. And that makes, we'll give an example in a moment, but that makes the energy modeler's job much more focused and effective. An aspect of Energy Plus that DesignBuilder mirrors is that you can allow a very highly detailed system description for anything that you're modeling, but it doesn't require it. Auto-sizing is one example, but templates are another. You can start with a generic description and then gradually refine it as you're developing the model into greater detail. The thing I like most, and which David actually just highlighted, is the unparalleled output quality checking or quality control that Energy Plus allows. Literally, you can look at every temperature and humidity condition throughout an air loop or within a zone. There is pretty much no end of detail that you can apply to your output and gain a much more clear understanding about whether your model is doing exactly what you intend. I describe it that in a typical energy model, you have literally thousands of inputs. How do you know that you got them all correct? You're not God, you're not perfect, and so the ability to review your output is crucial. And Energy Plus allows that. DesignBuilder through Results Viewer also allows it. I wish that was true 8 years ago, but I've learned a lot in the meantime, and some of the things I've learned here, that the above items are very valuable. This is an example of some of the detailed information that the GUI allows you to not think about, but I wanted to just touch on it because it's helpful to know what's going on behind the scenes, so to speak. Within Energy Plus, there is, as we already described, Matt was sharing, the outdoor unit, or the heat pump, is sort of the heartbeat or the main energy mover for a VRF system, but that air conditioner or heat pump is connected to a multitude of indoor terminal units. Within Energy Plus, you describe the terminal units, and that would be the zone devices that David just mentioned. Each of those terminal units has to be assigned to a terminal unit list, which is the list of terminal units that are attached to an air conditioning unit or an air conditioner unit. And then, by the way, since those terminal units reside in a zone and their fan heat, for example, contributes to the energy within the zone, you also have to assign them to an equipment list for the zone, which has further connections to an equipment connections item. And then, by the way, there's some pipe and height length inputs as well. These are not things you have to pay attention to at least you don't have to pay attention to how they're connected with Energy Plus, because DesignBuilder does that for you. But occasionally, when you're troubleshooting something, it's helpful to know that additional information. Modeling VRF, in part, as Matt mentioned, because it's a relatively new system or is not as widely adopted as some other systems, some of the challenges for modelers come from the fact that the VRF concept is not as well understood as some of the other HVAC systems. I think Matt gave a great explanation of what VRF does and how it's supposed to do it, and that helps anyone doing energy modeling know whether their model is both set up correctly and is operating as you expect. Another thing which we're going to touch on a little bit in a moment is that traditional or typical DX coil curves are not applicable most of the time to VRF. We'll see why in a moment. There is also the case that, and Matt touched on this, the indoor fan is much smaller and much less power than is typical for even nominally similar systems like fan coils or water source heat pumps. It's much less pressure drop, and so the fans are very small. And by the way, many of them, or most of them, seem to have speed control, so it's essentially a variable speed fan system. So that's another reason why the fan power is dramatically lower for these systems. The last item I'm going to touch on in the next slide, which is that occasionally a designer, because they don't understand VRF so well, has a poor mix for heating and cooling zones. This is an example. First, a little background. The upper left floor plan is from a 100,000 square foot facility, 10,000 square meters or so, and this level is below grade. The lower right portion is above grade, and there are not too many windows, but the back portion of the facade has a lot of windows, and there's a swimming pool over here in the extreme right end. The point I want to make is that in the design of this system, the designer made a specific effort to try and mix zones among the outdoor units, and I think though they missed an opportunity, probably inadvertently, but you can see the light blue area, that's a zone or some indoor units connected to one outdoor unit. Similarly, these other blue zones are all connected to the same outdoor unit. And then the sort of pink color is yet another outdoor unit, and that same outdoor unit is also connected here in the upper level. If you think about the way these zones are connected, and we'll just start with the pink, this is a below grade floor. Everything in the pink area is essentially a core or an interior zone. There are no exterior exposures except a little bit here and at the lower level, but that's adjacent to earth, so it's not exposed to the outdoor conditions. Similarly, in the upper level, this is a completely interior zone with perhaps a little bit of roof exposure, but this outdoor unit was a heat recovery style. How much heat was it recovering? I don't think very much. And if you apply the same logic, the blue zone is all core because it's adjacent to earth, not the outdoors. Here's an interior zone. This is mostly interior with a little bit of perimeter wall, but there's a little perimeter wall with a little glazing here. So all in all, these two units were, although they were specified and installed as heat recovery heat pumps, they didn't achieve their potential because the mix of zones wasn't so effective. We're going to now discuss, this is moving into more black belt territory, why curves are cool. As Matt already showed, this is a different representation of a typical cooling capacity curve for the Mitsubishi last generation equipment. And each of these colors represent a different indoor wet bulb condition. And apologies to the North American people, this is in Celsius because Energy Plus thinks in Celsius, and so I use it frequently. So this is the representation. And you can see that the key difference between this curve and a typical curve is that there's a distinct change between what we'll call the low condition shape of the curve and the high condition shape of the curve. And by the way, there's a boundary condition that is at a different point depending on what the indoor wet bulb condition is. So there's really three different curves represented here, one for the low condition, one for the high condition, and a third to represent where that changeover or that segmentation or inflection occurs. That's and as already mentioned, this sort of shape for the curve applies for cooling capacity, heating capacity, cooling power, heating power, and so there's three curves associated with each of those four. That's 12 curves. And then there are others for part load ratio, piping height, piping length, and then the indoor curve or the indoor unit. So there's a lot of curves here. We're going to discuss, David touched on this, you can represent this performance with a single curve. That's the red line. And by the way, and it just showed one out of the 5 different indoor wet bulb conditions. But that red curve is not a bad representation of what's going on if you ignore the very high temperature portion here. So that's not a bad representation. And so for this particular cooling capacity ratio, a single curve representation is a reasonable approach. However, this now is the cooling power ratio. And you can see that the inflection is a little more pronounced, and a single curve representation misses a fair amount of performance difference between, say, 10 Celsius, which is 50 Fahrenheit, and say 30 Celsius, which is 86 Fahrenheit. So there's a gap here between the purple line and the red line, which in this case shows that if you use a single curve, the Energy Plus will predict higher power than what the equipment actually requires. And by the way, that's a lot of hours during a typical weather year. If you have a moderate climate, this could be 1,000 hours easily, maybe more. So for all of those hours, you would underpredict or overpredict actually the amount of power, and you'd underpredict your savings. This is another example of now for heating capacity. Once again, there's a pretty sharp inflection for what actually occurs for the capacity of the heating mode of the equipment. And if you apply a single curve, it doesn't reflect what's actually going on. And so the key aspect of Energy Plus is that it allows you to make one segment for low, one segment for high, and you define the boundary condition so that you reflect the actual performance in capacity or power, you reflect it correctly. I'm going to give sort of a sidebar example about the importance of curves, and I'm going to use what is it's a definition by the American Heating Refrigeration Institute, AHRI, called either IPLV, which is the older part load performance term, and then IEER, or Integrated Energy Efficiency Ratio. You are probably aware, you need to be aware if you're going to be a black belt, that the EER is a single point rating condition and it's the peak summer condition. So it's at 35 Celsius, which is 95 Fahrenheit, and 67 watt bulb, 19.4 Celsius, indoor wet bulb condition. It's a single point. So at that single point, you define efficiency. Guess how often the equipment operates at that particular condition? For many installations, it never operates at exactly that condition, and 35 Celsius or 95 Fahrenheit occurs for maybe a couple of hours a year for many climates. Now, what happens for the, and by the way, the solid line is an IEER value of 11, and let me just stop for a moment. EER is defined, and actually Matt referenced it in his slide, it's BTUs per hour of cooling capacity divided by the input power in watts. So it uses different units, BTUs per hour on the top and watts on the bottom. So that's why, since you're dividing by, I won't explain that. However, it generates a little larger number. So the EER of 11 is so much capacity in BTUs per hour divided by the watts of input power. And input power is actually the compressor power plus control power, which is normally very small, plus a fixed test condition fan power. So it includes all of the power elements at that particular test condition and according to the AHRI standard. So an IEER of 11 derates to say 80% of the energy input ratio, or it's a number that reflects the amount of power for the capacity. And IEER of 15 has a hugely improved performance in power compared to the IEER 11. And so this is a big deal. If you haven't reflected this correctly in your curves, you will not get a good reflection of the actual performance in your energy model. So this applies to every DX coil, but the same principle applies to VRF coils, in particular because of their unique curve. In the case of a typical DX curve, it has sort of a single curve representation works well, but you have to apply the curve coefficients well. The last slide, I'm going to just mention that sort of as a big picture here, what we're trying to do is say that certain things matter more in an energy model, and certain things matter less. Just generically, I put this together for a presentation on existing building energy modeling, and as you can probably appreciate, it's always key to have the major blocks in the window areas shown correctly, but doors often are a very minor portion of the facade, and so they don't matter nearly as much as getting the major elements and dimensions right. And by the way, it doesn't matter if you get the length and width of the building right within 1/10 of 1%, because the envelope itself doesn't normally have as big an impact as some other aspects. In an existing building, you need to define major elements like whether the walls are lightweight or massive, and whether there's insulation or none, whether there's single or double glazed windows, but the glass coatings might matter, except they're harder to understand or harder to measure for an existing building if there are no drawings. And the point of this tabulation is that when you're doing an energy model, you need to reflect which are the key elements that will make my energy model perform or predict with the best accuracy. It's never going to be exactly the same as the real building, but you can make it closer and more true to the reality. And in the case of VRF, I think the key elements are to get the performance correct, and particularly EER and especially the curve representation. It takes more work to create all of those curves, but once you do it, say for a particular manufacturer, those curves are pretty close, and using a tool such as the spreadsheet that David mentioned, you can easily make changes, and it doesn't take an extended amount of time. So that's all for my portion. I hand it back to David.
Jim, many thanks for your black belt explanation of the finer points of VRF curves, and thanks also for distilling your experience on the value of all the different variables in your last slide. That's our presentation complete, and we'd now like to open the webinar to the audience for questions. We already have a number of text questions, but if you want to submit more, we'll do our best to answer as many of them as we can in the next half hour or so. Please remember to tell us who you'd like to answer the question, Matt, DesignBuilder, or Jim. We'll start reviewing the questions now, and we'll be back to you in a very short while.